We have spent two very large sections of the course talking about electricity, right? When we opened up talking about electricity in the first place, I really described that, hey, there's four forces. You already know one of them because it was gravity. There's a strong and a weak force, but we're not going to talk about those. But then the last one, and the one that we understand the best, is electromagnetism. And so far, we have really forgotten the second half of that word. Right? We have been completely focused on electricity the entire time, and we have not brought up magnetism at all. You might have played around with magnets. I'm sure you have. I'm sure you have fridge magnets and all sorts of other things. It's one of those early toys. Magnets show up everywhere. Right? They're one of those big things. They're a meme at this point, if I'm being completely honest. Right? Magic gravity for metals. It sounds like old troll science comics or something. And it's of course not true. We understand what it actually is, and we'll get to that point soon enough. But the magnetic field and the electric field have a very strong similarity between them. And the reason for that physically is because they're actually all part of the same force. But, let's look at the historical perspective here. We understood electricity and magnetism pretty well as separate concepts long before we understood what was actually responsible for that electric force and responsible for that magnetic force. We knew what charge was, but we didn't know what it was coming from. So that was a little bit of an issue, right? Because we have a lot of conventions that use these ideas that maybe don't necessarily work all the way. But we're going to kind of take that perspective to start with. At the very end of the course, we'll talk about really how they're one and the same, but for now, we're going to treat them as if they are separate fields, separate forces. They just have some relationships between the two. But a very watered-down version of this is that magnetism is essentially some rocks like to hang out with other rocks, and they like to hang out so much that they will literally smash themselves together. Right? And sometimes if you're playing with magnets, sometimes they'll want to spin a little bit before they do that, but they will want to be as close as possible. And it's not just that they would do this only when they're very, very, very close, but, you can do this from a pretty far distance away. If you have a couple magnets on hand or anything else like that, you can kind of wave a magnet somewhere nearby and you can make the other magnet wiggle around a little bit without necessarily being right up against it. So the long-range force, and that shouldn't really be a surprise here. If I keep telling you that electricity and magnetism are very similar things, then it only really makes sense that they're both long-range forces going as 1 over r squared, right? That at least makes sense to me. And some of these points, I'm not going to cover too much in detail. This is kind of like a very, very, very brief overview, but one of those points, that point in blue, I'm going to talk about towards the very end here. But not yet. Let's instead talk about what this equation actually looks like. So it's determined by the Biot-Savart law, right? If we remember, the Coulomb law was the electric force equation, or the electric field equation, depending on how you're looking at it. The Biot-Savart is the same thing, but for magnetism instead. And if we break this apart, there are a lot of similarities. In fact, what I would like to do here is I'm going to write out the electric field equation. I know you guys know it by now, but I want to take another look just in case because I really want to highlight some of the similarities. So we've got 1 over 4 pi E naught Q r hat over r squared. So let's start with the similarities. We've got like a 1 over 4 pi E naught thing. We've got a mu naught over 4 pi. That's similar-ish. Right, I think that's a pretty similar kind of deal. We might remember, probably not, but we might, remember that E naught is called the permittivity constant. And I've brought this up before, that there is a neighboring value called the permeability constant, but for magnetism. Right, the E naught is for electricity, the U naught's for magnetism. And it, again, is kind of small and everything else, but it's rearranged a little bit, but mostly the same. We also see a dependence on charge, right? And that's an important deal because the charge will determine, it has a hand in determining the magnitude, but it also has a hand in determining the direction. If the charge is positive, it points one way. If the charge is negative, it points in the other. We also still have our r squared, right? And that's the point that I was highlighting before. But we've got something different when we're looking at the direction. In the magnetic field, there's one more quantity that we actually have to worry about here, and it's velocity. And that's a little strange. Forces so far have not depended on velocity. If we're remembering all of these things, friction didn't, gravity didn't, I guess air resistance did, but the magnetic field is an air resistance. So this one's a little bit strange. And what this is really saying is that a moving charge creates a magnetic field, but not just any charge. Let's file that away for now. I'm going to bring this point back up sometime later, right? It's going to be a little while before I talk about this one again. But I do want to bring this up sometime later when we're talking about how the electric field and the magnetic field are really one and the same. So we'll come back to that point. But for now, we just need to focus on the fact that it is V cross R hat. That is a cross product. And what I'm trying to say here in this paragraph that I've got below is that the cross product is a very, very, very common thing to see. We are going to continue seeing cross products for as long as we're dealing with things in magnetism, right? Which is from here on out. So we're going to be continuously seeing cross products for the rest of the semester. It's just a common thing that we're going to see, right? Every magnetic equation has a cross product floating around in there somewhere. But the last thing that I've got on this one is that we've got all these different quantities and everything else, R hat, V, whatever all these things are. But then finally, the units for this thing as we see them are going to be Tesla, right? And not measuring in units of cars. It's a specific physics unit. But we'll talk about what are expected values in just a little bit here. So, before we get too much farther, I think it's worth spending a little bit of time reviewing how we deal with the cross product. If you were taking an algebra-based physics course, you would see this equation in blue, and that would be the only thing you would need to worry about. Right, remember that we're taking, essentially, anytime I take two vectors, there are two different possible angles I can take between them. I've got the small vector, or the small angle, and I've got the large angle all the way around the outside. The large angle on the outside is the one we are not going to consider. We don't need it. So anytime you're talking about doing this cross product, AB sine of theta, where theta is strictly 180 degrees or less. Never more. But anyways, this is a pretty easy way to describe what the cross product is, right? It's a lot like the dot product. It's just using sine instead of cosine, and the direction's a little bit funky, right? We might remember the right-hand rule as being the thing that dictates what direction that resulting vector would be going. So that's fine, though, assuming that you know the magnitudes and the angle. And there are a few different ways that you might use this right-hand rule to actually find the direction. Method 1, Method 2, Method 3, just as we see them on the page right here. I think Method 1's a fair one. I use that one sometimes. Where the general idea is if I have A and B going along two of my fingers, the result is going to be pointing in the last direction. Right? So if I were to have A, then B, then the rest of my fingers would point directly up from my palm, and that would be my last direction. We like to use the right-hand rule because, as you can kind of see, it's a little bit difficult to see three-dimensional spaces on two-dimensional sheets of paper. So we run into this issue sometimes. Method 2 is one that I'm going to talk about a lot more today because I think it's a really useful one in a lot of different scenarios. Method 2 is essentially this idea that if I have A cross B, my fingers curl in that direction. The direction my thumb points is the direction of the result. So if it's A cross B, then it would be going up. If it's A cross B, then it's going, well, into the camera from my perspective. But into the page is what we would say for that one. I like that one because the little difference between them is that I think the first method doesn't do as well when you're talking about non-perpendicular vectors. But, you know, however it works, I think you can still do kind of something similar like that. If I had something like this where you can see that's like a 45-degree angle between my fingers, I think that still works out pretty well. And then you just have to remember that these other fingers always stick out from your palm. The last one is one occasionally somebody I know uses this, but the screwdriver one I think is, I guess if you work with tools a lot, that might be helpful to you, but I work with tools a fair amount, and I can't say that it's a particularly useful visualization for me. But it's there. If it works for you, more power to you. But it's all three are really trying to say the same thing, right? They're trying to show that relationship between all these directions. So, whichever method you prefer to use, although I'm going to line up B here, they all start with the first step. Use your right hand. And I'm highlighting this because I really do think it's important. And I tell this story, and some of my friends come back and watch my lectures later or something like this. They will probably already know this story, but for the sake of it, I was in a 400 level physics course. So this is not a course for, typical engineers or anything else like that. This is a course for majors, specifically majors that are in their third or fourth or fifth year of the major. Experienced physicists at this point. 10 minutes into a class, a student disagreed with what was written on the board and said, I think that should be negative. I'm pretty positive that should be a negative sign. I saw the writing on the wall. I stood up. I walked out of the classroom. I went downstairs. I had a coffee maker in the basement of Krieger. I started a pot of coffee, let it brew. I had a massive mug, filled it up with half the pot of coffee, went upstairs, hang out in the lounge a little bit, chat with some people, finish my half pot of coffee, go back and fill it up the rest of the way, realize that I've been out of the classroom now for 45 minutes, walk back into the classroom, and the argument's still going on. I sit down, kind of zoned out. 5 minutes after I sat down, they said, oh, whoops, I was using my left hand. Nobody's above this. Nobody's above this, but be very careful. What I'm going to recommend here is that anytime you're doing this, we think some of what the issue is that if you're a right-handed person and you're writing with your right hand, you don't want to set down your utensil, you just use your left hand real quick and you go like this to imagine what that shape would be. Do not use your left hand. Do not use your left hand. It doesn't work. It's called the right hand rule for a reason. If you need to use the right hand rule, do me a favor, just no matter what, set down the utensil, then try to do the right hand rule. That's step one. If you can do that, the other steps are much easier. But we see this constantly in students from all levels. No matter how experienced you are, you have used your left hand for the right hand rule at least once. It happens. But try to be careful with it. But that's my big public service announcement on that one. Use your right hand for the right hand rule. And then these steps are really just describing what this is, but in bullet points. So, let's try some of these things out. We have three different pairs of vectors. A cross B, C cross D, and A cross B, but they're different. What I want you to do, at least for the first two, is see what you can do to find the magnitude and direction, with these being in or out of the page, for each of these pairs. Okay, so let's take a look at this one. This one's going to be very, very quick because I know the angles between these already, so it doesn't make any sense to go through what we're about to see in a minute here. I'm just going to take this equation exactly as we've got it. I'm going to plug in those magnitudes, I'm going to plug in the angle, I'm going to call it a day. So, for my first one, A cross B, that's still in highlighter mode. A cross B, magnitude of A, times magnitude of B, times sine of the angle between them. I'm expecting this to be 21.2. What direction? Well, let me take method one, for example. If I line my thumb with A, my index finger with B, so from my perspective, but I do recommend do this yourself right now with me, A, B, C should be going into the page, right? As I've got this thing and I'm trying to do like, here's roughly my 45-degree angle, something kind of like that. And I know that this is all reversed and a little bit strange, but that's why I'm saying do this yourself right now, right? Try this with your own hand. A cross B should be going into the page. If I were to go through method 2 instead, then what I would say is A cross B, thumb goes into the page. That's the direction we expect out of this first one. For my second one, I'm in luck. I see a 90-degree angle, and sine of 90 degrees is just 1. So C cross D is just going to be 24. Direction from C curling to D should be coming out of the page. This one is in, this one is out. So between these two, A and B. Okay. Part C. Let me try and plot this out. So let's imagine that I've got, here's my y-axis, my x-axis, and I'll have z going kind of like this. So vector A would be going 3 and 1 in the y direction, so maybe something like this. And then B would be going 3 but -2 but +2 in the k direction, so maybe something like this. And can I find that angle easily? No, I cannot. Not in any, like, I could do it, but I'm going to take the rest of the lecture if I want to do something like this. Maybe that's an exaggeration, but it takes a long time to do. It's awful. I don't recommend it. When we have vectors that look like this, there's a better way to do things. But before we can get into that, we need to go through a little bit of a gauntlet real quick and talk about some old linear algebra stuff. And I think, hopefully, if you took 191 with me last go around, we did end up talking about this, but it has been some time. So that's why we're going through this again now. But anyways, here's the idea. If I were to find a determinant is something that I do to a matrix to get out some sort of quantity. If I had a matrix A, B, C, D, then I could find my determinant by taking AD minus CB. If I wanted to find a 3 by 3, this is a little bit more difficult. I have to take it in order. What I would have to do is I would have to say, okay, start with A, cross out this, cross out this. What I'm left with is a constant A times the determinant of a 2 by 2 matrix. So that's A times determinant EFHI. Then for the next one, I would say, okay, well now I'm on an even number, so it's a minus sign. Cross out this, cross out this, cross out this. Now I have B times DFGI. And then finally, I would look for C, cross out this, cross out this. And I would see C times DEGH. And that would be a plus because I'm back to an odd number. And I would get this long equation right here. This is messy, I realize. So if we were to do this with A cross B, the determinant that we set up is top row is our unit vectors, I hat, j hat, k hat. Second row is our first value, so the 3 components of A. The next column down is going to be, or the next row down, sorry, should be the components of B. So it goes unit vectors, A, then B. Then if I were to expand this, we might notice something. So there's one of 2 ways to handle this. I can either memorize this formula down here, or I can know how to set up this matrix as is. I have done both. Nowadays, I think I like the matrix more, but let me talk about why. Let me point out one more thing that we might see in this before we go all the way into it, but we might notice that when we're dealing with this cross product, the x direction has no dependencies on the x components. It's only on y and z. If we look at the y direction, it only has dependencies on x and z. If we look at The z direction, it only has dependencies on x and y. It's an interesting thing in cross products, right? What it's basically saying here is that the cross product is maximized when my two vectors are the most perpendicular to each other, even if they are not just pointing nicely along two axes. This is maximized in each direction when those other directions are maximized as well. So you can memorize this formula. I don't know if I would recommend it. There is a pattern to it that's a learnable pattern. It's yz minus, well, if I'm talking about in terms of a, there is a pattern to these things that you can learn if that helps you learn the formula. I know the pattern pretty well. I use the pattern sometimes, not super frequently, but there is a pattern to it if you'd like to learn that. But what I'm going to recommend is not actually using this pattern either. What I'm going to recommend is something that I've got highlighted down here called Cramer's rule. Cramer's rule is a very, very easy way to deal with 3x3 matrices. Let me demonstrate. If I wanted to find the, well, I need to find the cross product, right? Which means I need to set up a determinant. So I'm going to say A cross B is equal to, let me set this thing up first. So this is I hat, J hat, K hat. Second row is my components of A, so that's 3, 1, and 0. Third row is 3, -2, and 2. For Cramer's rule, what I'm going to do is I'm going to repeat my first two columns. So I went I, J, K, I, J. 3, 1, 3, -2. Now what I'm going to do is I'm going to do almost exactly what I did with my 2x2 here. I'm going to take this row down, this row down, and this row down. That means I hat times 1 times 2 plus j hat times 0 times 3 plus k hat times 3 times -2. Then I'm going to subtract my up arrows. That arrow, that arrow, that arrow. I'm going to put my directions up front, but that's going to end up with a minus k hat times 3 times 1 minus I hat times -2 times 0 minus j hat times 2 times 3. Zeros, zeros. Don't need those. Sort out the ones that are left. So I've got 2 I hat. J hat is -6. And then I have -6 k hat and -3 k hat for a total of -9 k hat. There is my resulting vector. I think this is the easiest and the fastest way to do this. And this is why I like to use the matrix method. Cramer's rule makes this determinant easy. Versus this. This is a much easier way to do it. I know it takes up a little bit of space, but I think it's well worth it. And I think color coding it like this also helps. You can look up Cramer's rule. I don't think it's something that's very well discussed in the book. There are different pages that will discuss it, though, that go over it, but it's more or less this right here. You just have to be able to expand this thing out so that you can get 3 down, 3 up, and then take those as is. Down is positive, up is negative. So, let's try this one for ourselves. Follow the same method. It's what I'm going to recommend. I'm not controlling how you're solving these problems, but it's what I recommend, is to use that same method, try it out for yourself, see if it makes any sense. But let's go ahead and find the result of A cross B with these two vectors. Okay, so let's compare what we've done and make sure we're all on the same page here. So, as I've got this thing, I'm going to set it up in just the exact same way. A cross B, easiest way, set up the determinant. I, J, K, 2, 3, 0. B looks very similar, so it's again 2, 3, but now with a 2. I want to repeat my first 2. So I keep going in order. IJK, IJK, IJK all the time. That's the only order that we're going to take. We're never going to flip these. We're never going to use something else. So 2, 3, 2, 3. Now, I'm going to color code these because it makes it a little bit easier for me to see. 1 arrow, 2, 3 going down. I've got my IJK. So I'll have I hat times 3 times 2. Then I'll have j hat times 0 times 2. Then I'll have k hat times 2 times 3. Then I take my arrows up, and these are all going to be minus. So minus k hat times 2 times 3, minus I hat times 3 times 0, minus j hat times 2 times 2. Okay, get rid of everything with zeros. Then in order, the only thing that survives from I hat is this I hat times 3 times 2. So that is 6 I hat. Then my j hat minus j times 2 times 2. So minus 4 j hat. And then I have plus k times 2 times 3 and minus k times 2 times 3. So 0 k hat. Or we can just leave that off. Either way. But this is my resulting vector. Now, what would change if I had B cross A? Think about that. What would change if I had B cross A? Are there any guesses from chat? What would happen? Signs would flip. And that's it. And we can make that argument from the magnitude, actually. Because if we go back to the magnitude, what we were saying here was that, okay, well, it's A, B sine of theta. If I flip the order of these things that I'm doing, it's still the same theta. The only difference is that when I'm curling my hand, it goes one way or the other. So the sign would flip, but the magnitude should be the same. And what that means in a problem where we have all these vector components is that B cross A would give us negative 6 I hat plus 4 j hat. Can't we use the left-hand rule if you want to flip the direction? On a technicality, there are places where you can use the left hand. I do not ever recommend it. I think it is much simpler to always focus on the right hand. And then if there's a negative sign floating around somewhere from charge or something like that, then you can flip it, but you're consistently using the right hand to figure out where that cross product should go. Because it's one of those things, if I'm scared to open Pandora's box. Because if you're like, oh, the left hand could be used for some things, and suddenly there's ambiguity of when do we use the left hand, when do we use the right hand. Technically, there are places that you could use the left hand, but I'm never going to recommend it. It's some dangerous waters. If I were to put B in the middle instead of the bottom, that would be effectively doing B cross A. I would find exactly what I just found by just flipping the sign. It's a wonderful thing. The math just works. It's a neat little connection between the two, though. So it's consistent, at least, right? Everything's consistent was what I'm really saying, that there's not There's not some way that this all breaks apart or anything else. If we did B cross A instead, the order of the two bottom rows would be reversed, and we would get that exact same answer that we just wrote down. So, now that we've had a little bit of a run-in with the cross product, let's come back to this Biot-Savart law, and let's talk about what's going on here. We've got some different pieces that we might end up seeing, right? So one of the things that we've got, we are not just doing A cross B every single time, right? We are doing V cross R hat. So, as always, this should come as no surprise. I am going to recommend drawing out the picture. That shouldn't come as a surprise to anyone at this point, but I do still have to say it because I know a lot of people don't want to. What I'm going to do then is I'm going to draw from the charge to the point. That is my direction of R hat. Then I would take my velocity, find the angle between the velocity and R hat, should that be a simple thing to take, and I can just use my magnitude description. And then because R hat is a unit vector, remember that the length of I hat, the length of J hat, the length of R hat, whatever unit vector we use, all of these, they're always length 1, and it's a unitless 1, because a unit vector's only purpose is to provide direction, not length. So when we're finding this cross product, if we know that angle, the result is always just going to be some sort of V sine of theta, which if we're just looking for the magnitude, this could simplify that formula quite a bit, right? But realistically, that is not so different from just what we have up top here. It's just if you're looking for magnitude only. So, a quick reminder on our notation as we do these things, because now we are talking about 3 dimensions. We have to worry about the into the page or out of the page. And the way that we notate that is that if it's coming out of the page, it's an arrow. Right? So if you're looking at an arrow coming straight at you, which hopefully you're not that unlucky, but if you're looking at an arrow coming straight at you, you see the head of the arrow. It's a dot. If you're watching an arrow leave, you're seeing the tail feathers. So that's where we get this, and this should say, just for clarity's sake, it's an arrow. That's what it is. So hopefully that helps to, helps you remember what that difference is. So keep in mind, we just went through all this determinant stuff, not because it's useless. We are going to hopefully have a lot of problems where we can use the simple description, but there will occasionally be problems where we need to go through the determinant method. The determinant method just makes everything so much easier to deal with if you have messy vectors. So with all of that in mind, I want you to try this one. Oh, y is out for q is greater than 0. As we're seeing this, in this picture right now, right-hand rule would tell us for a positive charge, and try this with your right hand. If my charge is moving like this, the right-hand rule would tell me that if I went V cross R hat, then my B field would be pointing out of the screen. It is not a always kind of deal. This is for this picture specifically. For this thing right here only. If Q was negative, it would flip everything. That's what we're trying to say. An example of what we would expect from this particular picture. So, for this one that we've got right here, I have a proton moving directly along the x-axis going at, we'll call it lickety-split speed, 10 to the 7th meters per second. We're looking for the magnetic field at these 3 points relative to the origin. At point A, at point B, at point C. So this is one that it's pretty easy to do with just finding the angle. I don't recommend determinant for this problem in particular, but if you're feeling up to it, you could try it anyways. All right, team, let's start taking a look at this one. So I'm going to copy this thing 3 times. Let me put this on a new page first, so we're not looking at old things. Oh, there it goes. So I want to copy this thing 3 different times because we want to focus on each of these 3 points. I'm going to draw on this a little bit, so I want to make sure that it's as clear as possible. If we can actually move the picture, there we are. Make it a little bit smaller. Bring it down here. Bring it down here. So, focused on part A. At point A, that means I don't care about this, and I don't care about this. My r hat vector goes from the charge to the point. Kind of like this. What is the angle between r hat and v? Or I should say v and r hat, because that's the order that we're doing the cross product. What is that angle, though? Zero. Correct. There is no angle between these two. They are completely aligned, and sine of 0 is 0. This cross product is 0. If I am looking at my equation for a magnetic field, mu naught over 4 pi q v cross r hat divided by r squared, it's 0. That's it. That's it. Which is an interesting deal, right? Because it requires a moving charge, but it's not in front of the moving charge. Kind of by extrapolation here, it's not behind the moving charge, it's to the side. The units of this are Tesla. Part B. Now we've got some real work to do. So let's get rid of this. Let's get rid of this. Let's focus in on what's going on here. So my r hat vector is going like this. I wanted that to be in orange, please, so it sticks out a little bit more. Pointing up like this. That just so happens to be a right angle between v and r hat. That makes this a little bit easier. Since this is an easily describable angle, since I have descriptions for both of what these vectors should be, v cross r hat would be equal to v times sine of 90 degrees is equal, oh, let me be careful here. I should pull the direction from this, right? Because I have two vectors coming into a cross product. I should expect a vector to come out, and I don't want to be too sloppy with my notation. I set down my utensil. I prepare my right hand, not my left hand. I go from v, curl to r hat. I'm expecting this to be coming out of the page. My magnetic field coming out of the page, going along the positive z-axis. So, that should give us a positive k hat. That's what we see for that cross product. So then, and I'll go ahead and do this in red. If I'm looking at that B field, as I've got this thing now, mu naught over 4 pi q v cross r hat divided by r squared. Plug in all of my numbers. Permeability is one of our constants. V cross r, we have just found. Q is of a proton, 1.6 times 10 to the negative 19 coulombs. What I should find at the end of the day is 1.6 times 10 to the negative 15th k hat Tesla. Let me try and make it look like a 15. Or, if we're looking at our canvas questions, 1.6 k hat femto Tesla. Femto is 10 to the negative 15th. This is tiny. This is really tiny. This is incredibly tiny. When we're talking about magnetic fields, we are not expecting large numbers here. And I'm sure this number has been broken, but for a little while, I want to say the strongest magnet we had in the world was 34 Tesla at University of Florida in their mag lab. The one before that, which I think 21 Tesla or something like that, was actually strong enough that they levitated a frog inside of it. They, and you can find this video online of, they found a frog in one of the ponds outside. They put it inside of this thing. The iron in the frog's blood was enough for the magnetic field to levitate it inside of the magnet. And I only bring up this story because the frog, they took it out. It was a little bit panicked, but they took it out. It was totally fine. They set it back in the pond. What happens after that, I don't know. But I say that as 21 Tesla is a lot. An MRI machine is going to be on the order of 6 to 8 Tesla. And the reason that you need to immediately inform them if you've had any surgeries that would put metal inside of your body or something like that is because it will rip it right out of you. You need to be very careful with that. 6 to 8 Tesla is enough to take that office chair from across the room and send it flying. You have to be very careful with magnets that strong. It also takes a ton of power, which is why they are often like actively cooled and all sorts of good things. It's a massive coil of wire is what that actually is. So that's kind of what we're expecting, right? If I'm talking about like a fridge magnet or something else, I might consider, I'm going to guess, don't quote me on this, but I'm going to guess that a fridge magnet might be micro Tesla by the time it's attached to the fridge. But I'm not solid on that one. I don't have a confirmation of what that number should actually be. So keep in mind when we are talking about that unit vector, a unit vector is unitless. And it's always a length 1. So there will never be a conversion to be made. Now, I bring that up, but there is another way that you could write out this equation. I see this done sometimes in textbooks, but I'm not always a big fan of it. One of the ways that you could write this equation, specifically the cross product, is that piece right there could be written as V cross R vector divided by R cubed. It means the same thing. Because of how we define the unit vector, this means the exact same thing, but I think it's a little bit less intuitive when we're talking about that 1 over r squared dependency. I think this is a little bit more confusing to talk about that magnetic field, but it is another way that you can write out that equation. So, we've got one more here. Part C. Let's erase the things that don't matter to us, so let's focus on C. Let's draw out my r hat vector, and I should specify here, one thing that I didn't do last time that I should do right here. Let's specify that this point is at 0, 1 centimeter, 0. This spot is at 0, -2 centimeters, 0. I'm going to make this whole thing a lot easier, though. Can we all agree that it's, again, a 90-degree angle? Can we all agree that now it's going V cross R, so it's going into the page. It's going along the negative z-axis, like that, relative to what I see here in my picture. So V cross R is equal to negative V k hat. But then the speed is the same. The charge is the same. The direction is, flipped, but V cross R is still the same value. The only thing that is different is that our radius, our distance away between the point and the charge, has been doubled. Take this answer that we found from part B and say, hey, wouldn't you know it, it's just a quarter of that answer. Answer C should be equal to 0.4 femtotesla, or specifically negative 0.4 femtotesla k hat. Actually, I should probably move the k hat to the inside here. So negative 0.4 k hat femtotesla. Save yourself a little bit of work. See those similarities between different parts. The question that I was waiting to see if anybody would ask that one If something has to be moving to create a magnetic field, how do things like fridge magnets keep magnetic even when they're still? So, we actually have to go to chemistry for this one. What do we know about atoms? What do they do? What do they have floating around them? And how do they float around? It's not the sea of electrons part that I'm interested in. But there are charges floating around every single atom. And specifically, so if I'm not talking about those sea of electrons that are allowed to freely flow, the valence electrons, if I'm focused in on the core electrons, electrons have spin to them. And I know I've talked about this before, that spin is one of those kinds of things, if it's not actually spinning around, but it kind of is, but not really, it's in a weird middle ground. What happens here is that a magnetized material has all of the electron spins pointing in the same direction. You can magnetize a screwdriver by attaching a magnet to it and waiting for a while. Because over time, that magnetic field is pulling on all of those magnetic dipoles of the atoms and slowly pulling them all so they're all aligning in the same direction, right? When they're all scattered every which way, there's no net magnetic field, but when they're all pointing in the same direction, now we have some continuity. Now they can grow upon each other. So then, it's actually kind of funny because there's a couple different ways that you can demagnetize objects. The couple ways that you can demagnetize objects, one of them is to flash a magnetic field back and forth. So it goes one way, and then the other way, then one way, then the other way. And if you do that fast enough, you'll demagnetize something called a degausser. One of the other ways is to simply heat it up, because if you heat up something, then there's all of that random sporadic motion, and suddenly it's not just pointing like this, it's slowly buzzing around like this, and it loses that net magnetic direction. The last one, and I think the most entertaining one, is to literally just beat the snot out of whatever you want to be demagnetized. Concussive force does the exact same thing that heating does, just a little bit more violently and a little bit more loudly. But that's how. And different materials are magnetic because some materials are okay with lasting like that. You have different sets of material like ferromagnetic material, and this is something that I'll talk about next time as well. But ferromagnetic material means iron-like. Iron will hold on to that direction even after the magnet is gone. You have... Oh, geez, I'm getting all of this mixed up. You'll have paramagnets, which will line up while there's another magnetic field there, but don't really care once there's not. So certain objects might be attracted, might be weakly attracted while there's a magnet there, but otherwise they just don't care that much. I think copper is a good example. You can't magnetize copper. And then finally, you have antiferromagnets, which actually are very unhappy to see other magnetic fields and will reverse their direction instead. Superconductors get into a whole other business with what they do with magnetic fields. Superconductors get very, very wacky. But yeah, it's very cool. And I'll talk about that next time as well, because we technically have a lab next time. We'll get into that. I'll have to talk about that one next time around. But excellent question on that one. Nobody asked in Section A, and I slid away without having to answer that one. I could kind of leave the suspense building a little bit longer. Okay, so let's imagine, what if we had done this but longer, right? What if we found a lot of different points instead of just the one? What would we see? Well, if we were to take everything together and we looked at all of these different points along the x-axis, along the y-axis, along the z-axis, all of these different points, what we would find is a bunch of loops. And this is an important point. Magnetic fields always come in loops. Never as monopoles, right? If I think about like an electric charge, if I have a positive charge, my electric field points away from it, right? That's what I would call an electric monopole, because there is a source of the electric field. Whereas if I had a negative charge, it would be like a sink, because all of the electric field lines would go into it. and, I mean, sit in the center, right? It goes into a point. Magnetic fields always exist as loops. And that's that point that I tried to ignore earlier. Magnetic monopoles do not exist. You might have heard of like North Pole, South Pole when you're talking about magnetic fields. It's not just something about the Earth, and funnily enough, the Earth is actually reversed. The magnetic field, the south pole of the magnetic field is where the Earth's North Pole is, but that's beyond the point here. Magnetic monopoles do not exist. It always appears as a loop. It always appears as a dipole. Even the Earth, who we can kind of model like this. The magnetic field coming from the Earth rises up, goes down, and comes back in, kind of like this strange kidney shape. Oh, and I've got that direction wrong. If I just said something like that, it should be going like this. But the magnetic field of the Earth is also a loop. Magnetic fields always come as loops. Now, one thing that you might find useful when we're talking about these magnetic fields is that you might notice, but there is another right-hand rule that describes how this goes. Take your thumb and line it up with the velocity of this charge. Your fingers curl in the direction of the loop. If I go this way, like from my perspective at least, I'm sure it's backwards for you because again, you're looking at me on camera here, but if you try this with your own hand, you'll see that it does indeed match up. If I look at the thing going into the page, I have to go like this, kind of, but the curl does again match. On the technicality point, this is one of the spots where the left-hand rule could describe a negative charge, but again, I don't want to bring up the left hand. I like to focus on the right hand, but for continuity's sake, I did want to bring that up. That is one of the places you could technically use it. But anyways, this is how you can find the direction of the magnetic field, just knowing what direction the charge is moving. It's a very useful piece. So, with this, you should immediately have a little bit of insight. You should be able to look at this thing and say, hey, I know what direction the charge is moving. I know what direction the magnetic field should be. But I do recommend going through the problem anyways. Just use that as a sanity check. Make sure all of the values, all the directions agree. But this is something kind of similar to what we just saw, but now we're at a little bit of an angle. So, draw this picture out. Please draw out where R hat should be going. Think about what R should be. And let's find this magnetic field. All right, so let's go ahead and take a look here. Copy this thing all right on over. Shrink it down just a little bit so it's manageable. Something like that. Something like that. Okay, so we're going to draw all over this thing. First things first, I do want to draw what R should look like. So going from the charge to the point, just like that. And then if we were careful with it, we would also know that the R goes from the charge to the point, just like that. So there's my R vector. So if I wanted R hat, it's going to look like this, right? And it's just, it doesn't matter how long it is, because again, it's always length 1. So then my angle between these two, between V and R hat, is 135 degrees. I might notice here that this is 45. Should probably draw that a little bit better. So this down here is 45. To make the full 180 gives me 135. So V cross R, whoops, not R, R hat, should be equal then to V sine of 135 degrees. And then let's think about the direction real quick. We know that if we have a velocity going along the direction of our thumb, my fingers wrap around in the direction of the magnetic field. That tells me that this magnetic field should be pointing out of the page. Coming right for us. So, V sine of 135 positive k hat, which should just be V root 2 over 2 k hat. Okay, Now the only other thing I need to find, if I'm looking at this big equation right here, is I'm going to need to find what R actually is. So I see 2 centimeters by 2 centimeters. It's a right triangle. Then I can say that my R value is 2 root 2 centimeters. But really, that actual value is 0.0283 meters. So let's go ahead and take that value. Let's plug it in. Let's plug in what we have just found for a cross product. We are still dealing with a proton, so that is 1.6 times 10 to the negative 19 coulombs. Plug in all of these numbers together, and what we should find at the very end. Oh, come on. What we should find at the very end is 2.83 times 10 to the negative 16 K hat Tesla, or again in femtotesla, 0.283 K hat femtotesla. And that's what we've got. Well, if there are no questions or anything else, I think we will call it there for the day with 29-1. Next time, we start to look at this with a few more charges involved. And we'll see what that does to all of this mess.